It's a pleasure to introduce Albert Gnadt, and on behalf of his committee and his advisors. So Albert got his bachelor's degree in mechanical engineering at the University of Wisconsin-Madison in 2015, his SM in AeroAstro here at MIT in 2018, and is now, as of today's defense, hopefully in process of getting his PhD in aeronautics and astronautics. Has done a variety of things, worked in several labs within the department, and this thesis work is really the result of Albert's work in the Julia lab, advised by Alan Edelman and Chris Rakaukas. I'm just sort of the honorary chair of the committee as the AeroAstro person here, but Alan and Chris deserve all the credit for the academic advising and the research guidance. But most of all, Albert deserves the credit, and really excited to hear what he's going to tell us about today. So Albert, please take it away. The floor is yours.
Very much. And you mentioned Alan and Chris, but I think the real people to thank are the people on the Lincoln Lab side and the Air Force side. It was really a collaborative effort. It's been about 12, 15 of us working on this project. And I've done most of the actual coding, but there's been a lot of guidance from a lot of people. So I'm thankful to those people. I guess we'll get into that later. I actually want to mute. Sorry, I left it like this so that I can mute everybody. And then I gotta. All right, so nobody's gonna be able to talk until I unmute, I believe. Just FYI, but we'll do some questions and whatnot later on. And then I gotta change this quick. Uh-oh. Sneak peek. Uh-oh. Great. All right, now we should be set. Sorry about this, guys. A few things I got to do here. All right. Great. Okay. So thanks for the introduction. And thanks for everybody that's here. I see a good amount of my friends that were on before I started, and we'll see probably some people coming in. And if you have any questions, you can put them in the chat, but there'll be a Q&A later on. So you can save them till the end. And I have 60 minutes to present. So about 20 after, 25 after, this should wrap up. And then we'll do the questions and answers after that. And then there'll be a private deliberation following that. And I first wanted to thank my committee, Yusuf, Alan, and Chris, who have been doing committee meetings and one-on-ones for the past couple of years, 2.5 years really. And then my readers, Aaron Nielsen and Alan Wolber, who had the tough job of reading a 200-page document. And they've also been involved with the project and given me a lot of feedback. Sorry. There we go. So I'll start with an outline just so you have an idea of what's coming up. And so we'll start with an introduction, as is typical. And then I'll introduce the overall research question that I've been trying to answer throughout this project and introduce the contributions that I'm making towards answering that question. Then I'm going to introduce MagNav.jl, which is a package I've developed that I've done all the rest of the work in. So it's kind of a setup for the rest of the talk. Then I'm going to go into the actual models, aeromagnetic compensation models. You'll learn what that is in a few slides. And then I'll go into navigation, which is the thing we really care about. And then I'll recap and talk about future work. Then you'll notice in the lower right, I kind of figured a lot of people would be joining virtually. So I went ahead and put a link to the slides inside that link, along with all my citations are in there if you are curious. And then there's some fun stuff you might want to check out. So let's set up this problem. The real issue is sometimes GPS isn't available, and very specifically, GPS jamming is a real issue, and the US government is pretty concerned about it. And just as an example, shown on the right there, oh, sorry, my mouse is on the right there. That's an article from last month. So it's an issue that's occurring right now, and there's something we want to do about it. And so in this case, one option is to do magnetic navigation. So instead of relying on a satellite to give you information, you use the Earth's magnetic field to get information. And just as an FYI, jamming is basically when you send the same frequency signal as what GPS is sending, and basically the receiver gets confused. And then magnetic navigation on the opposite side, it is very difficult to do that type of thing because the magnetic field dies off with the cube of distance. And so that means you have to be very close to wherever the measurement point is in order to really corrupt it. If you're too far away, there's just no way you can corrupt the signal. And on the map, you'll see magnetic anomaly map, and you're probably wondering what is an anomaly. And we're going to go through that in the next few slides, so don't be too confused. And so just to give you an idea of kind of what the process is for doing this magnetic navigation, basically there's some initial position, say where you have GPS or some other way of knowing where you are to start with, and then you lose that information. You no longer are able to know exactly where you are, but your aircraft still has an INS, which is an inertial navigation system. And these have been around for a while. The moon landings used an INS, that type of thing. So you have that, but it drifts over time. And so your errors in your navigation position increases over time. And so what you can do is you can correct your INS using a magnetic signal. So you use magnetic measurements to correct that. And basically what you're doing is you're taking measurements and you're comparing it to a map, a known map. And again, it's called a magnetic anomaly map. And so again, you're probably a little confused. What is this anomaly thing? And so I'll start off with, there's 4 components really of any magnetic measurement for our purposes. And the largest one is the core field. And this is what you guys are all probably familiar with. It's the large magnitude portion of the total field measurement. So it's about 50,000 nanoteslas. You probably have no idea what that means, but it's 2 to 3 orders of magnitude larger than all of the other components. And so if you have a compass, that's what you're really measuring. That's where north is pointing. And the thing about the core field is it's very well modeled. For my work, I used something called the IGRF, which is a harmonic model, 13th order harmonic model. And it works very well and it's very accurate. And so we know the core field as a function of position and time to a very high accuracy. And then the next component is temporal variations, and these are basically space weather, so things occurring in the upper atmosphere that also are part of the signal, and it's very small scale. You can see it's 10 nanoteslas in comparison with 50,000 nanoteslas, and these temporal variations can either be measured at a base station on the ground, or you can also just account for them with the navigation algorithm, which we'll look into a little bit later on. And then finally, we're at that anomaly field that I've kind of been hinting at. And the scale of that is about 100 nanoteslas. So it's not as big as the core field, but it's still noticeable. And the anomaly field is basically what's left from a total field measurement when you get rid of the core and temporal variations, if there's no other corruption. And the anomaly field is more or less the crustal field of the Earth. So you can imagine the rock bed has its own magnetic signature, and that's what the anomaly field is. And the thing about it is it's pretty static over time. It might vary like 1 nanotesla a year or something like that. So it's pretty stable. And so if you have a map of the anomaly field, it lasts for a while and you can use it to navigate. It has enough frequency information to navigate. But then we get to the real issue, and that's the platform effects I'm calling it in this presentation. I might also call it an aircraft interference field or aircraft field or corruption field. And the platform effects really vary based on the type of platform you're using. So for a geosurvey aircraft, which is the type of aircraft that's actually used to generate the anomaly map, the errors are pretty low. They fly in a magnetically quiet operating condition. And so, you can see that the errors are about 10 nanoteslas, whereas a fighter jet, something that's really operational, might have errors of over 1,000 nanoteslas. And so it's a real issue. And just to kind of explain where these errors come from, basically the geosurvey aircraft, it has effects, I'm terming static effects, which are more or less observable effects and permanent, induced, and eddy currents are the subtypes of those static effects. And we're going to see a little bit more about what I mean by those in a few slides. But then there's also temporal effects, and these are more or less stochastic effects or unobservable effects. And that's from something like a control surface or an engine that isn't observed by the state-of-the-art models. And so just a quick summary, so you have an idea of these magnetic fields. Again, the core field dominates, and the anomaly field is what we really care about. It has a large amount of spatial variation, and it also has a lot of high frequency variation, and so it can be used to navigate. And it's also very stable. The temporal variations are just kind of there. You can either use a base station to measure them and subtract it off, or you can just account for it in the navigation algorithm because it's low magnitude. And then the platform effects, like I was referring to, they vary significantly based on what platform you're using. Okay, so what do we do about these platform effects? Well, I'm going to jump into kind of the overall MagNav kind of system diagram here. So you basically start with some sort of sensors. So an inertial navigation system, like I mentioned before, and you also have magnetometers, which are just measuring your magnetic field. And you feed that sensor information into your aeromagnetic compensation model. And the aeromagnetic compensation model, which is kind of the key thing I'm doing for this project, for this work, it basically removes that aircraft interference. It removes the platform effects. And then you feed that signal into your navigation algorithm. And like I mentioned before, you have a magnetic anomaly map that you're comparing the measurements to. And so we're going to kind of start with what is the state of the art? How is it done now? And so we want B Earth. So B Earth is that Earth field. Like I mentioned, we know the core field more or less. We know the temporal variations more or less, and we want the anomaly field. So if we have the total field and we get rid of the corruption, we're good to go if we have the core and the temporal variations figured out. And so that's what we want, the Earth field, that's desired. And then we have measurements. So B scalar is just a scalar measurement of the total field. And then you also have a vector measurement. And those terms, the A matrix uses various terms of the vector measurement. And we're going to see what this A matrix is in a little bit. It turns out to be a key part of this work. And then you have some coefficients as well, called Toll's Lawson coefficients. And again, we're going to get into what this is in a little bit. But the key thing here is that this term here is basically the aircraft field. It's the interference field that we're subtracting off from our measurement. And that kind of leaves us what we want, the Earth field. And so again, the total field contains all of these components. And unfortunately, you can't just measure one of the components. You have to measure them all at once. You can't pick and choose. And we have two types of magnetometers to do that. We have a vector magnetometer, which measures the magnitude and direction of the total field. But the issue with vector magnetometers is that they're inaccurate. At least 10 nanoteslas of error per component. It can be 100 nanoteslas per component. And so you can't really use it for navigation. It's not good enough. But we also have scalar magnetometers, but those only measure the magnitude of the total field. But they're very accurate. And so we want to use those for navigation. Okay, and so just out of curiosity, you might be wondering, how do we get those coefficients? I put them in red because it was kind of an unknown. And so we started with that equation on the right, the small equation on the right there, B Earth equals B scalar minus A times beta. And so we can use a trick. We basically put a bandpass filter on the equation. And if you use the correct bandpass filter frequency range, you can knock off the Earth field. Basically, there's not much frequency variation in that range for the Earth field. And so you end up removing an unknown, and you're just left with a simple linear equation that you can solve. And that's what's done in practice. They go out and fly a calibration flight and obtain measurements and then execute this bandpass filter. And then again, I was referring to this A matrix. It turns out these components are pretty important for this whole project. It's important for the state of the art, and it's also important for the models I'm going to be talking about. And I'm not going to go into the physics behind these terms. It's a little bit complicated. But the important thing is that there's three different types of components: permanent magnetic fields, induced magnetic fields, and eddy currents. And you can see that these terms are each kind of combinations of the direction cosines, the unit vectors of the total field measurement. All right, and so that model that I've talked about now, I've kind of gone through. It's called Toles-Lawson, and it's adequate for if you're using a tail stinger measurement. So you're measuring way on the back of a boom, and this is a geosurvey aircraft, like I mentioned before. But this type of aircraft isn't really realistic for military use, so we can't really do this method. It's not good enough, basically. And so we need a new compensation method where we measure it inside the aircraft and we're able to account for the interference. And so that leads to the overall research question. Which aeromagnetic compensation models will enable high accuracy airborne magnetic anomaly navigation while using corrupted magnetic field measurements? And so that's what I'm trying to answer throughout this project. And there's some contributions towards doing that. And the first one is MagNav.jl, and it's basically a suite of tools that are now open source as of today, actually, that are used for aeromagnetic compensation and for magnetic navigation. And I'm going to talk about all these, of course, throughout the rest of the talk. And then there's also linear models that I've kind of dove into, and a large evaluation of neural network models. That's contribution 3. And then online neural network-based aeromagnetic compensation, number 4. And then the last contribution that I'm listing here is adaptive filtering. It turns out to not really work that well. It's in the thesis, and I kind of talk about why I think it doesn't work. But I'm not going to probably include that in this talk. I have backup slides, but just for brevity, I had to cut something, you know. And I'm going to start with MagNav.jl, but I feel like I have to put a plug for the Julia programming language because my advisor is Alan Edelman, who's one of the co-creators of the Julia programming language. And so Julia is what I've used for this project. It's great, and it's improved throughout the years. I think it's about 10 years old now, and I've been in grad school 7 years. And so basically I've just kind of seen it progress as I've been here. The first time I used it, it was pretty buggy about 5 years ago, and now it's very nice to use, and it's very high performance. Okay, so what is this package, MagNav.jl? And so it actually contains a bunch of nice tools for doing this type of work. The first thing is you can import data or simulate flight data and INS data. And there's some open source data that's directly in the package that can be used. And that's actually the data I'm using for my project, which is nice because then the results should be reproducible in the future by other researchers. And then there's a bunch of map related functions that I'm really not going to talk about at all in this talk because it's not really part of my contributions, but I did spend a lot of time on it. So if there are questions, I have some backup slides if you're curious how these maps are generated and kind of the process. And then aeromagnetic compensation models, that's the key thing I've worked on. All of these models are in this package and they're all available, and anybody can try them out. Probably not anybody on this call, but they're available. And then the last thing is the navigation algorithms. Those are all available as well. And so I'm going to talk about the data on the next couple slides, and then I'm going to talk about the kind of baseline aeromagnetic compensation model and navigation algorithm. So the data that we're using for this project, at least currently, and what I'm using for the rest of this talk, was generated by this geosurvey aircraft. But we're not just using the tail stinger measurement. We also had multiple other measurements that were within the cabin. And so you can see MEGs 2, 3, 4, and 5. And 2, 3, and 4, and 5, very roughly the corruption increases from 2 to 5. And so 2 is very noisy and pretty much unusable, whereas 5 is pretty good and not too bad of a signal. And then we also have 4 vector measurements, A, B, C, and D. And it turns out that those all perform pretty much the same. B is the best because it's a little bit further away from the magnetic corruption that's by the engine and whatnot. But overall, they're pretty similar. And then in addition to these magnetometers, there's also inertial navigation system data and current and voltage sensor data that's measured within the cabin. And I'm basically terming all of this extra data as auxiliary data. And it's any data that's not cheating. So you couldn't use like GPS position or something like that as your auxiliary data, because that's giving you too much information. That's you're cheating. And the training data is all publicly available. Like I mentioned, it's available within the package. And then there's some testing data that's held out very much on purpose because we run a challenge problem as part of this project. And so we can't give it to the public because we want to evaluate their models privately. And so I'm going to have some results that are using that testing data. And I think I have a few that are using a portion of the training data to show results just so that it can be reproduced. And then I'll jump here into kind of the baseline approach. So I mentioned that MagNav.jl also has aeromagnetic compensation. So the baseline approach for that is Toles-Lawson, that model that we were going through earlier on. And then the baseline for the navigation algorithm is an extended Kalman filter. And you can see the states that we're including in the extended Kalman filter on the right. It's basically a standard Pinson dynamics model. So you have position, velocity, and tilt. And then you have some corrections for some of your sensors as well. And then the last state is that temporal variation. If you remember, we were talking about that earlier on in the talk. And I mentioned that the navigation filter can just figure that state out. And that's what S is in the state vector there. And so the kind of important part of the navigation algorithm for what we're doing is the measurement model. And so you have the IGRF, that's the core field measurement. And then you have your map, that's from the magnetic anomaly map. And then you have the temporal variations. And so you have those three Earth field components. And then of course, you need to do compensation on your actual measurement to compare with those three added values. And then just out of curiosity, you might be wondering how well the package performs. And so it was actually developed from some MATLAB code based on Aaron Canciani's work at the Air Force Institute of Technology. And it was hard to do a fair comparison with too many functions just because the packages have diverged a lot. And so it's not really a one-to-one comparison, but I did compare these ones just to see how well Julia is doing in comparison to MATLAB. And so basically we're comparing those two columns on the right for 5 different functions. And you can see for the computationally intensive functions, especially the last two, Julie's about twice as fast or over twice as fast as MATLAB. So basically it's really nice to use because you don't have to sit around and wait for things to run. It's very usable. And so we kind of have all this background established now. I guess we're about 20 minutes in here, and now we're going to really get into the meat of what I've been working on. And so, yeah, we'll kind of pause here, and we're going to start with the linear models. And there's nothing too innovative there, but it is good to compare with Toles-Lawson with a couple of more advanced linear models to see if we can make any improvements. And then we'll move on to the neural network-based models. We'll spend a lot of time on those. And then probably the funnest one is the online compensation, which we'll touch on third there. But to start with, I just wanted to mention, what are we trying to learn with these models? So, if you have a linear model, you have to try to figure out, you have to have some Y, you have to have some target value. And so for Toles-Lawson, we've already talked about this, you have a bandpass filtered measurement. And so I'm calling that, BPF. But for these other models, it's not that. We're not using a bandpass filter. And there's a few different ways. I show the core and the temporal variations in dotted lines because you can optionally subtract them off. But in this case, more or less what we're trying to do is figure out the actual anomaly field, the actual map value. If you remember the magnetic anomaly map, we're directly trying to figure that out. And so the truth value in that case is basically the stinger value, which we have. And then the last one is the difference between a noisy in-cabin measurement and the stinger measurement. So it's basically the aircraft interference field we're trying to figure out. So it's the delta between a good signal and a bad signal. and I'm terming that B aircraft here. And so Toles-Lawson uses the one on the left. The one in the middle, I use for some preliminary neural network evaluations, and I'll mention where I'm using that. But for the majority of the work, I ended up using the one on the right, which is probably the one I'd recommend people use in the future, trying to learn the actual compensation magnitude, the actual aircraft interference field. Great. So yeah, we're going to start with linear aerodynamic compensation, and I put one of the research questions that I was trying to answer here, and it's just, can we improve on the Toles-Lawson linear model with a different linear model? And so I've tried two different approaches. Well, I've tried other approaches, but I'm going to discuss two approaches. And the first one is elastic net-based aeromagnetic compensation. And so in this case, basically, you just put a penalty term on your equation. So it's similar to Toles-Lawson, but you have a lasso penalty, an L1 penalty, and that's good for, I forget if it's good for generalization. Okay. An L2 penalty, like ridge regression, L2 penalty good for generalization. L1 penalty is good for having sparsity. That's what it is. L1 sparsity, L2 generalization. And so we put these penalty terms on there. And the idea is that you don't overfit to your data, more or less. And the other approach I took is PLSR-based compensation, partial least squares regression. And that's kind of a more involved process. And I'm not going to go through all the equations here, but the basic idea is you're using latent input variables to find what's most correlated with the output. So you're not just relying on the input, you're seeing correlations between the input and the output. And again, you're just solving for some set of coefficients. And then let's see how well these perform. So the first table I'm showing, sorry, there's kind of a lot going on, but basically the rows here are different flight lines. So we're looking at different segments of flight. And I'm listing here the standard test data. I mentioned, there's some held out test data that isn't publicly available. It's those 6 lines right there. And then the last line is publicly available, and I'm including that for reproducibility by anybody in the public. And the thing to kind of see here is that Toles-Lawson is doing pretty good. So we're only using 11 minutes of flight day in this case. We're using what's termed a calibration flight. I'll actually go later in this talk, explain what that is more, but it's a shorter segment of flight, and it's what's done in practice, just doing a calibration flight and using that to figure out your coefficients. So Toles-Lawson is doing pretty good. And then there's another method called modified Toles-Lawson. I'm not going to explain what that is right now, but basically Toles-Lawson is the best, and ElasticNet and PLSR aren't doing too well. But then, if you use more data and you use this other method, it turns out that ElasticNet and PLSR are pretty good. And so in this case, they're kind of smoking Toles-Lawson. They're doing a lot better. And so the situation totally changed. And in this case, we're using, if you remember, for the ElasticNet and PLSR, we're using the difference between the stinger and the in-cabin measurement. So we're trying to directly learn the aircraft anomaly, the aircraft interference field, whereas Toles-Lawson is using a bandpass filter. And I think that's kind of the takeaway here is when you have more data, it makes more sense to use the actual aircraft interference field directly rather than trying to do this bandpass filter that has some error in it. All right, so that was the linear models. The next thing I'm going to talk about here is neural network-based aeromagnetic compensation. And so a couple sub-questions here are, can this approach, this neural network-based approach, outperform Toles-Lawson, the state of the art? And then also, if we use more information, those extra sensors I mentioned, the auxiliary data, can that improve performance as well? And so I'm going to start with, what is a neural network? And basically, what you're trying to do is use a neural network to model something that's nonlinear. So we were doing all linear stuff before. And kind of for the Wisconsin folk, I want to explain it. basically you have some inputs here. So in this case, cheese curds sold per year and cows per capita. And you're trying to learn something that's probably doesn't seem obvious how they're related. So in this case, Bucks playoff wins. And so, it could be a linear model, but it's probably highly nonlinear how those two are related. And so we want to use something nonlinear to do so. And so you put this fancy thing in there called an activation function. Basically, you have your inputs. Actually, I can go here. All right. Basically, you have your input here, and you multiply by some weight with a bias, and then it goes through an activation function to generate a nonlinearity. And that way you can model Buck playoff wins with cheese curds and cows. And so now I'm going to kind of get into, what are the actual neural networks that I'm using to do this aeromagnetic compensation. And the first model is just kind of a baseline standard neural network where you have some auxiliary data. I'm showing an example of how big this thing is with these green numbers on the bottom, just so you can kind of get a sense of the size. And so you start with auxiliary data, you feed it through the neural networks, that's the gray boxes, and you compare it with a target. And I mentioned the targets before, those three options. And so this is just kind of the vanilla approach, the most standard approach. And then, we wanted to try some more advanced approaches. We're doing a more scientific machine learning type approach. And that's where we get into these next few models. And so the first one is called model 2A. And so instead of learning the target value directly, instead we're learning a set of coefficients that get multiplied by that A matrix. We talked about the A matrix before. That's what Toles-Lawson involves. And then you multiply those, and that you compare with your target. So instead of learning one value, you're learning this A matrix times a set of coefficients. And then the second model that we looked at was, now you're trying to figure out a correction to Toles-Lawson. So Toles-Lawson is diagrammed up top here. You have your A matrix here, and then you have that bandpass filter of the two values, and then you get your coefficient. So this is all just regular Toles-Lawson up here. And then we have a correction down there in the blue box. And basically, we think Toles-Lawson does pretty good with the linear stuff, but the non-linear portion, it doesn't really account for as well. And so we want some sort of neural network addition to that. And that's what the C is. If you look at this equation down at the bottom here, this little correction term is what we're trying to use the neural network for. And then very, very similar is model 2C. But the main difference here is instead of just using some static Toles-Lawson coefficients, now we're actually updating them. So you'll see beta Toles-Lawsons. Oh, sorry, I didn't say this, but the red values are what the neural network is learning. Beta Toles-Lawson here is actually getting updated along with the additive correction. The nice thing about Julia is you could actually do this. You can put directly in your loss function both the neural network output and the coefficients as parameters, and it backprops through the whole thing and figures them out. So +1 for Julia for that reason. And then the last model is much newer. It's suggested by Chris Rakakis. And instead of doing an additive correction to the post Toles-Lawson, you kind of do an additive correction within Toles-Lawson. And so in this case, we're doing we're generating again a vector of values right here, and these are getting added to each Toles-Lawson coefficient. So the correction's occurring within Toles-Lawson. All right, so hopefully I didn't lose too many people there. I know those models, if you've never seen them, it can be a bit much, but basically there's 5 different models that I wanted to evaluate, and I guess we wanted to evaluate for this project. But one thing I haven't really talked about is what this neural network actually looks like. What are the layers, and what are the features that you're feeding into it? And there's kind of a large campaign to figure that out that I've been working on for quite a while. And the first thing is, how big should it be? How many layers should there be, and how many nodes per layer? So yeah, there's a lot to see here. There's a lot of different evaluations I did here with different layers and different numbers of nodes and even different activation functions. But the kind of key thing to see here is that these training values are pretty similar overall. And the testing values, they're generally is overtraining if you go to too deep of a model. And so I ended up just choosing five of them to look at a little bit further that I thought were performing pretty well. And so those are bolded. And then I looked at those a little bit closer, and I changed the optimizer, and I ended up doing some preliminary feature selection to kind of down select what features are going into this neural network. And ended up just using the smallest one that I thought performed pretty well. On the testing data set that I talked about before, those 6 lines, it's getting under 5 nanoteslas of error. And just for reference, under 5, you're doing pretty much as good as the Stinger. And so it's performing pretty well, and decided to stick with this small neural network. And then as far as the features, I went through a pretty in-depth effort in trying to figure out, what current and voltage sensors are important. Are there any other terms that are important within that auxiliary data? And so there's 4 feature selection approaches I ended up using, and those are these columns here. Basically, the first one is called drop column feature importance. And in that case, you train the model for as many features as you have, and you just remove an individual feature each time. So if you have X, Y, and Z, you'll train one time without X, one time without Y, and one time without Z, and then see how the model performs when you do each of those. And then permutation is similar, but you only train it once, and then during test time, you permutate the values, you randomly shuffle them, and again, see how well it performs for each different feature. Sparse group lasso is a lot like ElasticNet, actually. You're putting an L1 and L2 penalty on the first layer weights. It's another way to kind of send some of them to 0. You make some of them very small, and basically you end up deciding your feature importance by the magnitude of those weights after putting the penalty in. And then the last one is shapely values. And I'm not going to really go in depth on those, but it's from game theory, and you can just there's a package to generate those. And so, yeah, sorry, there's a lot going on here, but basically the feature importance, the values at the top are the most important, and the rows are sorted by the average of the 4 right columns. And just to kind of make things a little bit easier, the most important features are, of course, the scalar magnetometers, and in particular, the least noisy scalar magnetometers. So in this case, magnetometer is 4, magnetometer 5, and the difference between those two is what the third one there is. And then also important are the permanent and the induced terms of that Toll's Lawson matrix I talked about before, and basically that comprises almost all of the top 25 features. And then the one other thing to mention here is, I mentioned I'm sorting by the right 4 columns, and the reason for that is that these are a lot more similar. Like they're pretty much the same trends. Like the top 25 is almost exactly the same for these approaches for permutation, sparse group lasso, and Shapley. Shapley. Sorry, Alan. And the drop column approach is different. The values are, this is saying it's the 6th most important. This is saying it's the 101st most important. And so what's going on there is there's some correlation between the features. And so if you remove any individual feature, the model performance doesn't really change that much. Basically, there's something else that can kind of account for it. And so you end up with very similar performance for each evaluation with drop column. And basically, it's kind of just luck which ones end up at the top. It's kind of random, the features that appear the most important. And so for our project, for what we're doing, at least in this, for these features that I'm looking at, I would not recommend drop column feature importance. Now we can also look at what are the least important. So it's the same type of table, and we kind of want to see what's at the bottom of it. And so a bunch of the current sensors are at the bottom, and a bunch of the voltage sensors are at the bottom. And it turns out that really makes sense based on if you just look at the actual data, itself, if you look at the standard deviation, if you look at the skew of the actual data that's coming in, it totally makes sense that these aren't important. Some of them are nearly static values and honestly probably shouldn't have been even included in this analysis. And then the other thing is the eddy current terms, the third term of the Toll's Lawson A matrix. Turns out those are not really doing that much. And that's also true in general for Toll's Lawson. But for Toll's Lawson, there's not really a reason not to include them because it's a very simple linear model. Whereas these neural networks, you might not want to include it because you have to train with these extra terms that aren't really doing anything. And so basically, I ended up kind of removing the features that seemed least important. There was some subjectivity in it. I did have hard numbers, but at the end of the day, you had to put a cut somewhere of what's important and what's not. And so I did that, and I reduced the feature count to 77, and then evaluate each of the models. And here we're looking at how the training and testing errors kind of proceed for the number of training epochs. And the first takeaway is that they're all very similar. There's not a significant improvement, at least between models 2A, B, C, and D. I would say model 2C is probably the best here because it has the lowest error at an earlier training epoch. So this is basically equal to this, but it occurs much earlier, and then it appears that 2C might overtrain a little bit. But 2B and 2D also have this low error. So in this case, they're all pretty similar. The actual thesis has some other results that kind of back up model 2C being the best. And just to review what that one was, I know I kind of blazed through those models. So this was 2C. And so this is where we're generating this additive correction. And then we also have the linear portion from Toll's Lawson, which is also getting updated. You're updating the Toll's Lawson coefficient. So basically, you're learning the linear and nonlinear portions of the compensation kind of at once. You're doing them together, but you're also kind of keeping them separate. And it turns out that approach works pretty well. All right, so that kind of wraps up the neural network based approach. And the next one I'm going to talk about is online aeromagnetic compensation. And to start with, well, actually, I'm going to talk about these questions. So the questions are, how can online neural network-based aeromagnetic compensation be implemented? And then also, one thing I'm going to talk about at the end is, are there any type of maneuvers we can do with the aircraft as it's flying to use with this online approach? And so I'll start with kind of the linear version of online compensation. And basically the idea is you put the Toll's Lawson model into the navigation algorithm. And so in this case, we added some states. So before it was just these, if you remember, the last one was S, the temporal variation. Now we have these extra terms for the Toll's Lawson coefficients and for the vector magnetometer. And in this case, the measurement equation, before we had the RGRF, the core field, and we had the map, and we had temporal variations, and now we have this Toll's Lawson correction that's in the measurement model directly. And then we also have online neural network-based compensation, and this is what I really wanted to look into to see if we could get any further improvements by doing the neural network online version. And so it's kind of similar where we have the neural network weights instead of the Toll's Lawson coefficients within the state vector. And then one key thing I want to touch on is actually initializing this thing. It was something I spent a lot of time on trying to get this thing to actually work. And it turns out a recursive least squares to initialize the covariance matrix was kind of the key thing to get this thing running. There might be other approaches, but I just wanted to mention that. And then the other thing is I'm using minimal auxiliary data for this because of the computational burden of using a really large neural network. Basically, if your state vector gets too large, you can't really run it in a reasonable amount of time. So I have to limit the amount of auxiliary data. And so I'm going to show some smaller feature sets for that purpose. Great. And so I kind of want to just kind of review and see where we're at with this overall process. And the kind of thing to see here is it's pretty complicated. I'm not showing nearly everything that's going on, all the parameters and whatnot, But at a high level, the kind of inputs into the system are these green boxes. And so you have, and this is basically the INS over here. And then you have your magnetometers here, and then you have your map information over here. And then these blue boxes are the navigation algorithm, and it's cyclic here. It goes around like this. And then here are the states, or some of the states of the navigation algorithm. And in this case, we're including these neural network weights within the state vector. And so it's a pretty complicated system. And I just wanted to review for the Wisconsin folk where we're at and what I'm doing with this process. And so what I talked about before was putting this neural network as your aeromagnetic compensation, doing a nonlinear approach. And it works pretty well, but then we want to move to putting the neural network in the online approach, putting it directly in the navigation algorithm. And so that's what we've called an end-to-end approach for this project. In some circles, they also call it the exhibit approach. And so basically, we like neural networks. So we went ahead and put a neural network in your navigation algorithm. And so with that, I started with basically trying to match the Tolles-Lawson approach with the neural network approach. And to do so, you can just use the same Tolles-Lawson terms as your features and use a linear activation. There's a bias as well that gets added on here. And so it's doing the same as Tolles-Lawson compensation, but you're doing a neural network approach. And then I kind of ramped that up. So first I got that implemented. And then I went to this more complicated model where we have some auxiliary terms. And then I like the switch activation function. I've seen it performs the best. ReLU does kind of okay, but this is kind of where we're at. This is the approach we're taking. And I mentioned before using less features because of the computational burden. And so there's basically two small feature sets that I've used. And in the first one, there's 26 total features. We have a single scalar magnetometer, a single vector magnetometer, and there's 3 terms and 12 terms respectively. And we also have a direction cosine matrix and some current and voltage sensors. And basically, from the feature selection results, I kind of deemed these the most important features to include in this feature set. And then I wanted to look at, what if we don't include anything other than scalar and vector magnetometer? And so the first thing to see here is, so if we compare this green box and this green box, we can see that the performance is significantly worse or noticeably worse when you drop down the features, especially in using Meg4. So this is Meg3, Meg4, and Meg5. We're trying different types of scalar magnetometers. And so it gets worse if you get rid of the direction cosine matrix, current sensors, and voltage sensors. So this auxiliary data is actually doing something. It does provide some benefit. In some cases, it might not be worth having to have these extra sensors. It might not be worth the extra, nanotesla of error. And then the second thing to look at is comparing across the green and blue box here. Basically, the neural network approach seems to be doing much better than kind of the best linear model that I had, the PLSR. It seemed to be doing significantly better. And so now we want to see how these do in an online setting, like I mentioned. And so we'll start with just the INS by itself. I mentioned that the aircraft have these INS, and you can rely on it for navigation, but over time it's drifting. And so in this case, the easting error does kind of okay. It stays within about 100 meters of error, whereas the northing error, it goes up to 400 in this case. So for a lot of missions, that's not really suitable. It's not good enough. And so now we're kind of comparing, kind of busy plot, but we're comparing 4 different models. So the first one is Tolles-Lawson. That's the state-of-the-art model. That's what's done typically. Then we have more or less the best linear model that I had, the PLSR model. And then I have the best not online neural network approach, and that's model 2C, that's in yellow. And then the online version of model 2C, that's in black. And the cool thing that's kind of going on here is that the online approach appears to be getting rid of these big dips. It doesn't have this large divergence that these other models have. And so model online version of Model 2C seems to have some promise for doing navigation. And just for reference, that's about 32 meters of DRMS inaccuracy, whereas the Stinger, the thing measured on the back, which is very clean, does about 19 meters of error. And so we're not doing too bad using this significantly noisier magnetometer. I mentioned early in the talk, Meg 2 is the noisiest, then Meg 3, then Meg 4, then Meg 5. And so it's one of the noisiest magnetometers, and we're doing pretty well. And then I just wanted to compare with Meg 5, which is, not very noisy. And in this case, there's not really much benefit to going to this much more complicated model. The Toles-Lawson kind of state of the art does pretty well because there's just not that much corruption in the signal. All right, and it looks like I'm good on time, so I'm going to talk about these en route aircraft maneuvers. So I've kind of referred to the calibration box or the calibration flight a couple times, and that's basically this flight pattern here. They fly in a box literally, and then during the flight pattern, they do some pitches, they do some rolls, they do some yaws, and you're trying to basically put aircraft interference into the magnetometer measurements. You're trying to inject aircraft field noise into the measurements by doing those maneuvers. And then just for reference, what yaw, pitch, and roll are here. And this is from Mark Drella. I think it's important that every AeroAstro PhD cites him at least once. And then the first thing I looked at here with doing these maneuvers is, okay, let's treat each, oh, sorry, I didn't actually say, so there's 18 maneuvers that I looked at here. So you can do pitch only, you can do pitch and roll, or you can do pitch, roll, and yaw. And then there's different magnitudes of those maneuvers. So it's low amplitude, medium, and high amplitude for each one. And so there end up being 18 sets of maneuvers, with different types of maneuvers and different magnitudes of the maneuvers. And first thing I did was treat each one as its own calibration box, like you would normally use with Toles-Lawson, just to see how well it performs on some held out flight line. And the first thing to notice here is that the results are pretty similar. Like the magnitudes aren't that different from 1 to 18 here. But I do think that avoiding these large amplitude maneuvers is probably a good idea. Seems like those are a couple of the higher error maneuvers. And I do think that there is promise to doing these pitch and roll only maneuvers. These are some of the lower ones. And I'm specifically pointing to the high altitude version of the maneuvers because I think that's a little bit more accurate. Basically, it was run twice, once at a low altitude, once at a high altitude. At the higher altitude, there's less of a gradient in the magnetic field. And so your aircraft field is more discernible compared to the Earth field. There's basically less interference from the Earth field, and it's kind of the opposite. And then the other thing I looked at is actually doing navigation with each of those boxes and seeing how well the navigation algorithms perform. And in this case, I'm doing the kind of baseline model that I mentioned early in the talk with Toles-Lawson and an extended Kalman filter. And then I'm doing the online version of that in the far right column. And I think the takeaway here, is these pitch and roll only maneuvers seem to be doing pretty well. There is one outlier here. I couldn't quite figure out what was going on with that. But other than that individual value, which could have been due to a signal drop or something I didn't see. Other than that, they seem to be doing pretty well. So I think that there is promise to only doing pitch and roll maneuvers in flight to kind of improve your calibration in an online fashion. And the reason why that probably makes sense is that if you actually look at the pitch, roll, and roll and yaw for a calibration box, basically the yaw, it's right here. You're already doing yaw when you do each corner of the calibration box. And when you do your roll, you also have some yaw. So your signal already has yaw involved. And so doing an extra dedicated yaw maneuver isn't really giving you that much. But one thing is that the flight data for that was not the greatest. There were some issues with it as far as the actual magnetometer measurements, and they didn't quite execute it the way we wanted to. And so within the thesis, I actually made a recommendation about doing this again to provide more insights into doing this type of thing, because I do think the online approach is probably the direction to go for this project. And so if you're able to better figure out your calibration states, doing some sort of maneuvers, then we should figure out what maneuvers you actually need to do. And so that pretty much covers the main technical part of my talk. And I just wanted to touch on the contributions again. So I started the talk with MagNav.jl, talking about the actual software that this entire project was done with. And again, it's open source. And if you went to that link that I had, the short URL link, it actually has a link to MagNav.jl. And then I went through the linear models, kind of seeing that if you have a good amount of data, the PLSR or elastic net models are better than Toles-Lawson. But if you just use a calibration flight, Toles-Lawson is hard to beat. The neural network-based approaches tend to do better than the linear models in pretty much all cases. And then the online version of the neural network-based approach does seem to outperform the pre-processing methods of linear and neural network-based aeromagnetic compensation. And then again, there's a fifth contribution I'm not going to talk to. It looks like I'm at 55 minutes here. And then I do want to talk about future work briefly. And so the first thing is revisiting those aircraft maneuvers, like I just mentioned. And then the second thing, which is bolded for a reason, is obtaining the magnetic anomaly maps. Basically for this project, we had two maps, Renfrew and Eastern Ontario, and that enabled everything we did as far as navigation. It wouldn't really be possible to evaluate navigation without those maps. But for most of the US and definitely for the world, those maps aren't available, and they have to, these geosurvey aircraft have to literally go out and fly back and forth to collect that data. And so it'd be useful to figure out, maybe can we use commercial flights somehow to correct high altitude maps to a lower level or something like that. I discussed that a little bit in the thesis. And then for this project, we had 5 different magnetometer locations, but for an operational aircraft, you might end up using a wing-based location instead, and we just don't have any data on that. I don't have any data on that, though there has been some tests evaluating that with AFIT and whatnot. And so I recommend trying these models with those locations. And then one thing I was curious about that I just haven't looked at was how important is the pattern of the noise in relation to the map values? I haven't actually looked to see do the spikes in the noise correlate to the magnitude of the magnetic map values or anything like that. And I'd be curious to see how that affects navigation, the pattern and the noise. And then the last thing is real-time implementations of all the functions that are included in MagNav.jl. Right now, it's kind of research-based as far as evaluation goes, and there's going to be some modifications that are needed to make it ready for real-time use.